Hi everyone, and welcome back. This hopefully will be my last part, depending on how long this video is. So I'm going to just, continue hopping right into the problems. So for 17, we want to graph the following function. Looking at this function, we know that it is a polynomial, meaning that it's going to have a variety of roots. Now, since it's a quintic function at degree 5, that means there's going to be no real way for us to factor this, so the only technique that we have to find potential roots is doing our P over Q. Now, since this is in the calculator portion, we can just look at the graph in our y equals function in the calculator and kind of use it as a method to at least eliminate the possible options of what we think the graph may look like. So I'm going to state my possible roots here, 1 to 8, and my Q value is 2, so I'm going to divide that by 1 and 2. So my possible roots is every combination, so that's going to be all the whole numbers up top, and then 1/2 is my only extra option here. Now, if you put this function into the graph, you can kind of see that -2 is going to inherently be a root, and that positive 1/2 is going to be a root. So I'm just going to do the division knowing that -2 is going to be a root. And so it should work out. If it doesn't, then obviously I've read my graph wrong. So doing our process, remember that 0 is a placeholder. So it'd be 12, which gets me 4, which gets me -8. Okay, so we have one root. Now looking at the graph, because it actually has a parabola shape, if you put it in your calculator, you'll see that -2 actually has a multiplicity of 2, meaning I could actually do this one more time with -2. Okay, and then finally, like I said, it looks like my last possible root is 1/2, just based on what the graph appears to look like. And yep, that would be the case. So we have 3 roots, x plus 2 with multiplicity of 2, x minus 1/2 with the multiplicity of 1, and then I'm left with this remaining function, 2x squared minus 4. Now, we don't want to really leave this as x minus 1/2, so there is a way we can rewrite it, but we can actually kind of use the fact that this has a GCF of 2. I'm going to take out the GCF of 2, and I'm basically going to distribute it into this function. So I get x plus 2 squared, and now this function will be 2x minus 1, and this will be x squared minus 2. Now now that I have the roots of this and this term, I now need to get the roots of my final term, meaning I get the roots of plus and minus square root of 2, which is approximately 1.4. So in terms of my graph, I like to make my little table here, root multiplicity. The first one is -2 with multiplicity of 2, 1/2 the multiplicity of 1, positive root 2 with a multiplicity of 1, negative root 2 with a multiplicity of 1. So I'm going to graph those functions, those terms, -2, 1/2, and I'm going to do my best. And so the last part is determining the end behaviors, and since this is it's an odd positive, left goes down, right goes up. And then the last thing that might be helpful is my y-intercept. So my y-intercept is just going to be my final term here, which is 8. So my y-intercept is going to be all the way up here. So I'm just going to do my best. Now the key to this is remembering that if it's an even multiplicity, I actually don't go through. So in this one, if I go up all the way up there, my graph would look something of that nature. It would probably have a lot heavier dips in terms of the actual shape, but as long as you have identified the components of my graph and there's important aspects, I'm not going to focus heavily on how low a dip should go versus how high the rest of the graph would go. All right, so again, solving a function in interval notation. It's another inequality. Again, you do have access to a calculator in this portion. Okay, so again, there is really no way to factor this, but if I put this into the y equals form of the calculator, you can see that 1 is a root. Now again, if you're not sure, you could always do p over q, which is what I did. P is 6, q is 2. So that means my possible factors are this over this, which means my options are 1, 2, 3, 6, 1/2, and 3/2. Now again, fortunately for us, 1 is a root, so that's going to be a very quick one to work out. Six, there we go. And so I get x minus 1 times 2x squared plus 13x plus 6, which is factorable on its own. So 2x plus 1 times x plus 6. And so here are my three roots: 1, negative 1/2, and negative 6. A good way to check to make sure you've done them right, if they're all fractions or whole numbers, they should be out of that table or that list that you created. If you get something that's not on that list, there's something wrong with your factor. Now, if you get a square root, that's okay. So now we just have to test on my number line: negative 6, negative 1/2, and 1. And so this will be 0. I'll test 2, I'll test negative 2, and I'll test negative 10. And so I already have this done off to the side, but when I test them, I get negative, positive, negative, positive. And since I want everything less than 0, I want these two intervals. So my final answer here is negative infinity to negative 6, and then from negative 1/2 to 1. Oops, that's not what I meant. Okay, and then 19. So again, I can't solve this normally. I have to basically use common denominators. So this term here is going to get an x times 4 over an x times x plus 4. This term here is going to get an x plus 1 times an x plus 1. And so I'm going to rewrite it as x plus 4 minus 2 times x plus 1 over x plus 1 times x plus 4. And just by distributing and cleaning up the top, I get negative x plus 2 over x plus 1, x plus 4. So it's not as rough as it can be. But now I need to find my sort of number line components. So again, any vertical asymptote, which occurs at negative 1 and negative 4, and any x-intercept, which occurs at positive 2. So negative 4, negative 1, positive 2, and I'm going to test some points. 5, 0, negative 2, negative 5. And I end up with plus minus, plus minus. Now, one more thing about this. Negative 4 and negative 1 are vertical asymptotes, meaning I cannot include them in my final answer. So when I want something less than 0, I'm talking from negative 4 to negative 1 and 2 on, but I can't actually include negative 4 and negative 1 in my answer. So even though most of my answers should be bracketed here, because negative 4 and negative 1 are where the vertical asymptotes exist, we cannot actually do those in my domain. Number 20, find two numbers whose sum is 16. So let's just say I take x plus y, and I want that to be equal to 16, but has the largest product. Remember, product means multiply. So this is very similar to the fencing problem, where, if you remember, I want to try to find a maximum or a minimum, and I am trying to use two variables. The best way to do it is to rewrite one variable in terms of the other. So the product has to be x times 16 minus x. And so I get 16x minus x squared. And now I can just, use the vertex form, negative b over 2a. Since it's a quadratic, it might be helpful if I rewrite it in descending form, in standard form. So I get negative 16 over 2 times negative 1. So x is 8. And then if x is 8, that would also mean that y must also be 8. So those two numbers, 8 and 8, are the two numbers whose sum is 16 and is the largest possible product between every combination. And then the last word problem on this page, 2 boys watch the fireworks and don't like the noise. And the house is window that's 6 feet off the ground. So I always start by trying to draw something to help me visualize. So here they are. Here's I guess the window of the house. Yep, it's a terrible drawing, but that's where we're at. And so the fireworks are going to happen up here. And so the idea is if the firework is let off, right, this is sort of our trajectory. Again, the firework will explode before that. The question says, how many seconds will the rocket be above their window? Now remember, their window is 6 feet or 6 meters off the ground. And the rocket is traveling at a speed of 20 meters per second. So we have this equation, S of t equals negative 4.9 t squared plus the initial velocity of 20t. But the thing is, my initial height of my rocket is 0. I want to know when is the rocket's height greater than 6. I don't want to know what happens when it's launched at 6, because it's not launched at 6, it's launched at 0. So I have this equation, and I want to know when is this greater than 0 now by subtracting the 6. And through the use of quadratic formula, we get the 2x values, 0.326 and 3.756. Now, the last part to this is when is it greater than 0? Now, obviously, it's going to be the time in between them, just considering how a rocket launch would work. But if we were to place these onto a number line, we would get negative, positive, negative when we test. So it would be between the seconds. So we would say between 0.326 seconds and 3.756 seconds, which is a total of 3.45 seconds. And finally, on our last page here, the distance that a body falls from rest is directly proportional to the square of the time of the fall. So distance is proportional to the time squared. So that's going to be our generic form. Now remember, we're not done. We need to find a couple pieces first. So if I know that they're going to fall a distance of 144 feet in a total of 3 seconds, I can find my constant of variation here. So I do 144 equals 9k and divide both sides by 9. That gets me k equals 16. And so my distance would be 16t squared. Now that I know the amount of time for the next portion, that's when I can plug it in. So this person would fall 1,600 feet. The loudness of a speaker measured in decibels varies inversely as the square of the distance from the speaker. So loudness is equal to k over distance squared. When we are 8 feet from the speaker, the loudness is 28 decibels. So 28 equals k over 8 squared, which gives me a constant of, it's going to be a very large one when I multiply, 1,792. So loudness is equal to 1,792 over distance squared. And now it says, what is the loudness when we are 4 feet from the speaker? So we're just going to do the same idea here. Now that we have the constant, and the loudness is going to be 112, I think, was this in decibels. I think it's dB, actually. 24, heat generated by a stove varies directly as the cube of the voltage and inversely as the resistance. So heat varies directly with the cube of the voltage and inversely with resistance. The question says if the voltage remains constant. So this is not going to change. This is a constant. What needs to be done to triple the amount of heat generated? So I want 3H here. I'm not changing the constant. I'm not changing voltage. What I need to change is R. So we want to think about what would I need to do to R to make it that 3 times the amount. So there's basically 2 ideas. First one is that we could triple R, but if we triple the resistance, we'll actually be dividing by 3 times the amount. So since it's in the denominator, I actually want to do the reciprocal, where I need to do 1/3 of the resistance so that everything gets toned down and the heat will triple in volume. So we would actually do 1/3 of resistance. So this is more of a thinking portion of this problem. And then finally, a company is planning to manufacture wheelchairs that are light and fast. The fixed monthly cost would be $500,000 and will be an extra $400 per wheelchair. So we know that the fixed cost is $500,000, but it's $400 for every wheelchair. So this is just a plain linear model. Now write the average cost equation for the number of wheelchairs. So the idea is on average, I should be using X, not W, sorry, for wheelchairs. So this is the cost of all the wheelchairs. So to just get the average, I would take the standard cost. Actually, let me make that A, not C, for average. Would be the cost equation divided by the number of wheelchairs. So just think about, when you're taking tests, you want to find your average, you add up all the test scores and you divide by how many. So this is the same case. If I take the cost of all the wheelchairs and divide by the amount of wheelchairs, that will give me average cost. So now if I want to find the average cost of producing 1,000 wheelchairs, I would just plug 1,000 in. I'm going to let you do that calculation on your own, but we would just plug 1,000 into this equation. As well as vice versa, for the 10,000, we would just substitute in 10,000 as well. Okay, so I'll let you do those two. Last one, what does the horizontal represent in this case? So if I just think about the average cost of what is happening here, meaning if you notice your average cost for 1,000 should have been 900 for this first part, your average cost for your second one would have been 450. So what we're noticing is as the number of wheelchairs increase, the actual average cost begins to go down. And so what number is that going to approach? Well, the standard cost of the wheelchair. The idea is if I make enough wheelchairs, it's going to basically eliminate the monthly cost, because that $50,000 or $500,000, instead of being split between making 100 wheelchairs, is now going to be split between what it costs to make 1 billion wheelchairs. So what happens is the constant goes away, and so the horizontal asymptote in this case represents the cost of the cost of the wheelchairs after enough wheelchairs are made to basically separate. This is a really long explanation, you don't need it to be this long, to separate the startup cost. So I just want you to think that it basically allows us to separate that starting up cost and to make it less per wheelchair, which means the cost of a wheelchair is basically what we're going towards. Okay? Well, thank you. I hope that was helpful, and let me know if you have questions.